but not intended to explode, intended to remain sealed, constant volume. So your calorimeter constant is going to be C, which again is specific heat capacity, but it's the specific heat capacity, or the actually, not the specific, but the just heat capacity of the calorimeter. So if no heat escapes, then the heat gained by the calorimeter equals the heat released by the reaction. So Q of the calorimeter is the heat being absorbed by the calorimeter, is equal to that calorimeter constant times the change in temperature, which is also equal to whatever heat was lost from the reaction. So aside from the conceptual framework of how this whole reaction is happening, it ends up boiling down to, pun semi-intended, a specific heat capacity problem. And actually just heat capacity, because it's a calorimeter. So the calorimeter constant is just, in this case, 5.73 kilojoules per degree C. So for every degree C that the calorimeter increases in temperature, that's going to be 5.73 kilojoules of energy. So for this reaction, we have 1.550 grams of liquid hexane undergoes combustion in a bomb calorimeter, and the temperature rises from 25.87 degrees C to 38.13 degrees C. So find the delta E of the reaction in kilojoules per mole hexane. So the heat capacity of the bomb calorimeter, 5.73 kilojoules per degree C. So first we want to figure out, right, what was the change, how much energy was released. And this is another situation where you can also use just dimensional analysis. So we can say we've got our 5.73 kilojoules per degree C. And then we notice we have a change in temperature. This will be 38.13 degrees C minus 25.87 degrees C. Does this need to be in Kelvin, and does it matter? You can do it either way. So if you convert both to Kelvin first and then you subtract them, you'll get exactly the same difference between the two numbers. Huh? Yeah, actually, here I'll show you. So 38.13 minus 25.87. Seeing is believing, right? 12.26 degrees C, so that's the change. The key here is that you can't do the subtraction and then convert it into Kelvin. Then it'll be wrong. 38.13, and partly because our calorimeter constant is in degrees C. Plus 273.15. That's Kelvin. And that's 12.26 degrees C. This works because 1 Kelvin and 1 degree C are the same size. So any difference is going to be the same. So we can take that 12.26 though and multiply it by 5.73. So I guess I'll rewrite this. And that'll be 70.2498 kilojoules. But are we done? Not yet. Because this question wants us to find the answer in kilojoules per mole of hexane. So we just have the kilojoules. So we know for our 1.55 grams of hexane, we got out 70.2498 kilojoules. So we need to figure out, if we just had 1 mole, how much heat would be released. And we could do that by taking our 1.550 grams of liquid hexane. I guess I'll just C6, H14, and convert this into moles. So that'll be 86.2 grams of C6H14 is 1 mole. I think I left off some precision here. 0. And then that's going to be 0.0174 moles of hexane. And then if I take 70.2498 kilojoules, divide it by 0.01740. What? Did I just do the same thing twice? Wow. So it's going to be 4,037. How many sig figs do we have? 3. So we'll have to do 4.04 times 10 to the 3 kilojoules per mole. Questions? Yeah. Oh yeah, it's slightly off, huh? Huh. Could be oh, I missed a 5. This is a good object lesson in, so that like, this difference, and I think it should be negative. I mean, it should be negative, but this difference between 4.04 and 3.91 is so close that it's suggestive of a typo like this. So I did 1.50 grams instead of 1.55. I didn't do that on purpose. I mean, I totally did that on purpose, and you guys passed the test. So yeah, now we get 3,907. And yes, it should be negative because the reaction going forward releases energy. We know that because the temperature of the water increased. If it was positive, that means that the temperature of the water would have decreased. So not the, so always think of it from the perspective of the system, the reaction. In this case, yeah, it increased. Yeah. All right. So that's the bomb calorimeter. Are there any other questions? Okay. So we could also do this at constant pressure. So if we have a chemical reaction occurring open to the atmosphere or at constant pressure, energy can evolve both as heat and work These feel out of order for some reason, but often we are only interested in the heat exchange, not the work done. So the enthalpy of a system is the sum of its internal energy and the product of its pressure and volume. So enthalpy is a special sort of categorization of energy for a chemical reaction. And we include this pressure and volume because it perfectly cancels out the work being done. So there is some work being done, and we sort of acknowledge that fact and say how much work is being done and how much work, I guess acknowledging the fact that this delta E contains work and then accounting for that amount of work being done as the pressure and volume, because most things are going to happen in an open atmosphere. So if there's an expansion of gases, automatically work is going to be done. If there's compression of gases, then work will also be done, but in the opposite direction. And this inclusion of pressure and change in volume accounts for that. And then it also, sort of similarly to a bomb calorimeter, but using different techniques, lets us reduce this down to delta H being just the heat, but the heat being evolved at a constant pressure. And this is enthalpy. And enthalpy, just like the change in energy that we were talking about, is a state function. So it doesn't matter how you get to your final state. The only thing that matters is the difference between your initial state and your final state. So a lot of the times they'll be similar in concept and often in value. Delta E would be the measure of all of the energy, heat, and work. And again, delta H is just the heat exchanged under constant pressure. So the difference is the largest for reactions that produce or use large quantities of gas and therefore have a large change in volume. Under those situations, there's going to be a much larger portion of work being done, and we're just accounting for the heat here. So lighters, usually fueled by butane, when 1 mole of butane burns at constant pressure, produces 2,658 kilojoules of heat and does 3 kilojoules of work. What would the values for delta H and delta E for the combustion of 1 mole of butane be? So how is delta H different from delta E? Delta E is the total energy. Yeah, delta H is just the heat exchange. So we can eliminate some of these. Well, what can we eliminate? B. Yeah, we can eliminate. Why can we eliminate B though? Yeah, E can't just be the work being done. There's actually another one we can eliminate. Which way? Yeah. D, because this is a positive. That means that heat would be added to, this would be like, if this was the case, it would be cold fire. And so burning the butane would actually absorb 2,600 kilojoules from the environment. Not going to happen. Maybe I should write this, right? So delta E is equal to Q plus W. So if the system is doing work on the environment, is that positive or negative? Yeah. So it's taking energy from the system to do work on the environment. Just like if you were to push something heavy, it would take energy from you to push the thing. If you're the system, you're losing energy. You're expending energy. So delta H, or I mean, C is the right one because delta H is just the heat component, and delta E is the heat plus the work being done. Yeah. Any questions? Yeah? Good? Good? Okay. All right. Now we can take this and we can apply it to chemical reactions. So delta H and delta E are going to follow the exact same conventions. If one of them is negative, or if they're negative, then that's going to be an exothermic reaction. I guess I'm going the opposite of the slide here. If delta H or delta E is positive, that means that heat is being absorbed by the system, and it's endothermic. And then again, delta H is negative, heat is being released by the system. So anything you burn is going to be exothermic. The endothermic reactions are pretty rare. The only ones are like chemical cold packs. Yeah. Can't think of any other ones off the top of my head. Endothermic or exothermic process is a little bit different because it's not necessarily a chemical reaction happening, but could be a physical process also. So for example, in ice cube melting, is that going to be endothermic or exothermic? Endothermic. I always have to think about that one for a second, because what about water freezing? It's exothermic because it's losing energy. I think the thing that kind of always gets me also is that if ice is cold, so how could it be exothermic for water to freeze? But you have to remove heat from the water in order for it to freeze. It's actually part of the reason that they flood fields. Well, I guess part of that, if for citrus specifically, if it starts getting too cold, they can flood the fields, and then it adds all of this water, and then that water has a high heat capacity, and so it starts absorbing energy, and if it starts freezing, then it's exothermic, and it keeps the citrus from freezing also. So yeah, that one's going to be, but ice cube melting is endothermic. And then what would the sign for delta H be? Yeah, positive delta H. Oh, nail polish remover quickly evaporating after it's accidentally spilled on the skin. It's like oddly specific. Where's the energy going? Endothermic. Because it's taking heat from your body, which is why it feels cold, and then entering into a higher energy state. And so also going to be positive delta H. Gasoline burning within the cylinder of an automobile engine. Not a trick question. I know some of these feel like trick questions. Exothermic, yeah. So delta H, sign of delta H is going to be what? Negative. So something evaporating is endothermic. Again, the opposite of that process is going to be the opposite sign of delta H. So if you had water condensing, it's going to be exothermic. Or nail polish condensing, which would be to have really high pressure. But yeah, so always try to frame it in terms of the system and think about, do I have to put energy into the system for it to be able to do the thing, or is energy coming out of the system for it to be able to do whatever the process is? All right, so when we look at chemical reactions, so those are those are physical processes, aside from the gasoline burning. But we could think about gasoline burning for this, right? So an exothermic reaction gives off thermal energy. We've already covered that energy can't be created or destroyed. So where does that energy come from? So for the internal energy of anything, it's going to have kinetic energy, and it's going to have potential energy. And then the potential energy we can break down even further. So, right, gasoline burning, kinetic energy can't be the source, right? The gasoline could be cold, but it could burn and still release a ton of energy. Right, so if it was the kinetic energy, then it would have to be hot, and the temperature of the gasoline would change, aside from the chemical reaction, but that doesn't happen. So instead what's happening is, as the atoms rearrange in the chemical reaction, the potential energy, that's a typo, is converted into thermal energy. So we're taking these bonds between the atoms, breaking a lot of those bonds, and in the case of something that's exothermic, we're breaking weak bonds. The weak bonds don't take a whole lot of energy to break. So you have to put a little bit of energy in to break those bonds, and then new strong bonds are formed. And so those bonds are strong because they're in a lower energy state. And so to go from this weak bond to a really strong bond, a ton of energy gets released because it's more stable, takes less energy. And so you're releasing a larger amount of energy for making new bonds than it took to break the original bonds. So in endothermic reactions, it's going to be the opposite. You're going to break strong bonds, which takes a lot of energy, and then somehow form weak bonds, which don't take a lot of energy to form. So if an endothermic reaction occurs in a flask, what happens to the temperature of the flask? Endothermic reaction. Yeah. Temperature falls. Right? And in an endothermic reaction, we're breaking strong bonds. And forming weak bonds. And this is kind of why endothermic reactions, I guess this hints at why endothermic reactions are very rare, because why would you spontaneously break a strong bond and form a weaker bond? And that's a question that I don't think we really answer here. It has to do with entropy and the eventual heat death of the universe. So if you want to know more about that, look up entropy. Oh yeah, so you can do stoichiometry with this. And so again, remember, it's like breaking bonds, forming bonds, and the relative strength of either of those determines how much energy is either released or absorbed. And we can apply this to stoichiometry. So haven't we already talked about extensive properties? Maybe not. So for any chemical reaction, we can have a enthalpy of reaction or heat of reaction. This is an extensive property. So that means that the heat transferred, the amount of heat transferred, depends on the amount of reactants that react. So if you burn more gas, you get more heat. If you burn less gas, you get less heat. That's an extensive property. By convention, we calculate the delta H of the reaction for the number of moles of reactants in the reaction as written. So it would be, right, for 1 mole of propane, for 1 mole of propane, we would get out 2,044 kilojoules. Or for 5 moles of oxygen, we would also get out 2,044 kilojoules. And so this number here, the heat of the reaction or the enthalpy of the reaction, is in a stoichiometric relationship with the balanced chemical reaction. And so we can also do this for the reactants that are formed. So if we know this reaction is happening between propane and oxygen, if you can calculate how much CO2 is produced or measure how much CO2 is produced, you could also measure how much heat is released. And then that would be 3 moles of CO2 produced you would generate that much heat. And 4 moles of water produced, you'd also get this amount of heat. For example, if we consider the following thermochemical equation, what's the heat associated with the reaction of 6 moles of A? So how much heat is, well, yeah, what's the heat associated with just 2 moles of A? So if we have 6 moles, that's 3 times as much A. So 3 times as much heat also. And then the sign here would stay the same. So since we have a negative 51 times 3 should be negative 153. That's sort of the, I don't know what the better name of this, but just kind of like to look at it, sort of like intuit, deduce what it's supposed to be. You can also throw this into an equation and say we have 6 moles of A, and it's essentially stoichiometry. And for every 2 moles of A, we're going to generate negative 51.0, well, not negative 51, but I think you know what I mean. That'll be negative 51.0 joules of heat evolved. And so that'll give us negative 153 joules. And here, maybe, yes, technically 1 sig fig. Unless it's exactly 6 moles. All right, so another stoichiometric quantity. Can do this for something a little more complicated. If you've got, well, just a bigger chemical equation, essentially. Ammonia reacts with oxygen, according to this equation. So we can start with our 155 grams NH3. And what do we do next? Convert to moles of NH3. 14.01 plus 1.01 times 3. So molar mass, 14.04 grams of NH3. That's 1 mole NH3. There we go. Now what? Bingo. Negative 906 kilojoules on top. That's all there is to it. So 155 times negative 906 divided by 17.04 divided by 4. So negative 2060.299, and then 3 sig figs. So just stoichiometry. All right. Questions? Moving on then. All right, so I'm going to give you guys some time to work on this one. Essentially the same thing. The other way you could have done this, right? If you know one quantity, you can calculate anything. So we could have just gone from the 33 grams of butane and then calculated how much CO2 would also be produced. Should get you the same number, as long as you don't round anything. Might be slightly different, but should be within error. Kind of interesting that on this one you get 3 times, pretty close to 3 times as much CO2. Just coincidence. Cool. All right, so this is the calorimetry that you guys did. Constant pressure calorimetry. And that just measures the delta H of your reaction. So you only measured the amount of heat. Well, actually, you guys didn't even do a reaction, you just heated stuff up and put it into the water? Okay, well, if you poured something in and a reaction did happen, it would just give you the heat of the reaction. Right? When you're just mixing things or combining 2 things of different temperatures, there's not a reaction happening. There's only heat being exchanged. And I guess that does draw kind of a nice parallel. Because there's no change in volume at all of expanding against, even though you're adding 2 things together, you're not expanding against an external pressure. So there's absolutely 0 work being done in that. And so the delta H and delta E for that situation will be exactly the same. Yeah, so we kind of covered this. I guess it's slightly different. The same concept applies, though, that in your solution, when you mix the 2 things together, you're going to have some solution. You'll have the mass of the solution, the specific heat capacity of the solution, and then the change in temperature. And then you know that however much energy, right, because we're measuring the change in temperature of that solution, we know this and we know this. That tells you how much energy was added to the solution. And all of that energy, or heat, more specifically heat energy, all of that came from the reaction. And then that Q of reaction is going to be the Q, or heat, of the constant pressure calorimetry, which is that Q sub P. So the heat under constant pressure, which is the same as delta H of reaction. So all 3 of those things are equal. So if you calculate this, Q of solution, make that negative, that's your Q of reaction, and also your delta H of reaction. So it makes it kind of easy, makes it convenient to calculate. All right, so if we have 500 milliliters of a 0.1 molar silver nitrate combined with 50 milliliters of 0.1 molar hydrochloric acid in a coffee cup calorimeter, our temperature changes from 23.4 degrees C to 24.21 degrees C. Calculate delta H of the reaction. Use 1.00 gram per milliliter as the density of the solution, and the specific heat capacity of your solution is going to be 4.18. So specifically asks for delta H of the reaction. What are the units of delta H of the reaction? Delta H of the reaction does not have grams. Joules or kilojoules per mole. And actually, I mean, it is kind of written as just like kilojoules, because it depends on what you're calculating that for in the reaction, but it'll be stoichiometrically linked to whatever is in the reaction. So in this case, we'll be calculating it per 1 mole of silver nitrate or per 1 mole of hydrochloric acid. Both of those will work. We do need to know how many moles, but to even get to that point, we need to know how much heat. So that is going to be just Q equals MC delta T. And if the density is 1 gram per milliliter, what's the mass of our solution going to be? Yeah, 100 grams. There's 100 decimal grams. And then 4.18, that's joules per gram degree C, times 24.21, which is our final temperature, minus 23.40 is our initial temperature. So Q of our solution is 338.58 joules. So what's the Q of the reaction? Actually, yeah. I'm going to say back up a step, right? Because our temperature of the water increased. And so for the, I guess, solution as a whole, the temperature increased. And so that was an increase in heat energy of 338.58 joules. That had to come from somewhere. And it comes from, again, breaking of weak bonds, forming of strong bonds, releases excess energy. So the heat wasn't just produced out of nothing. The new bonds formed, releases that heat. And so all that heat, since it's coming from, let me see, I'll write it like this, Q of reaction. So it's all coming from the reaction. So this is the negative Q of solution. So if I plug in Q of reaction equals negative 338.58 joules. All right, so that's for the reaction, given all of the stuff that we have, and given that we have less than 1 mole of each thing. But what if we had 1 mole, right? How much heat would be released if we reacted 1 mole of silver nitrate? So what's the heat of the reaction? How do we find that? We start with the molarity. We want to find moles. Yeah, so we use the molarity to find moles. And we can use either of these. Since they react in a 1-to-1 ratio, and it's the same volume, the same molarity, that means you have the same number of moles of each. So this reaction, in theory, would go to completion. So I'm just going to use the silver nitrate because it's first. So remember, molarity is moles per liter. So if I take moles per liter, the 0.1 moles per liter times liters, so 0.05 milliliters, that's 0.00500 moles AgNO3. And now all we have to do is take negative 338. Well, actually, I guess not all, because that's in joules, divided by 0.00500. So negative 338.58 divided by 0.005. And that's 67,716 joules, which is the same as 68 kilojoules. Once we round for the correct sig figs. And this is a trickier one, but why are there only 2 sig figs? Yeah. So the change in temperature, I didn't write it down here, but it's only 0.81 degrees C. And since these each only have 2 decimal places, oops, go away, 2 decimal places, then we keep 2 decimal places as significant figures for that result. And then that carries on forward and means that our final answer only has 2 sig figs. Okay. So how is this different than the constant volume calorimetry that we talked about before? This is constant pressure. How's delta H different from delta E? Yeah, delta H doesn't include work. The work's kind of canceled out. Now in constant volume calorimetry, we make it so no work can be done, so then any work that sort of would be done, because it's trapped in a constant volume, actually kind of gets converted into heat. So the difference between your constant pressure versus your constant volume is one of them has that work included, one of them does not. So depending on how much expansion you get, how much work being done, constant pressure versus constant volume will be slightly different. Because here we could be expanding in a constant pressure situation, losing some of that energy as work. So, same reaction with exactly the same amount of reactant is conducted in a bomb calorimeter and in a coffee cup calorimeter. In one of the calorimeters, Q equals 12.5 kilojoules, and in the other, Q of reaction is negative 11.8 kilojoules. Which value was obtained in the bomb calorimeter? So is the bomb calorimeter constant pressure or constant volume? Yeah, it's constant volume, constant volume. So bomb calorimeter equals constant volume. Oops. And then the coffee cup equals constant pressure. And in the coffee cup, we're calculating delta H. In the bomb calorimeter, we were calculating delta E. So we just talked about the difference between delta E and delta H. So which of these two results, 12.5 or 11.8, is going to be from the bomb calorimeter? Why A? Yep. So A would be the bomb calorimeter, B would be the coffee cup calorimeter, because you lose some of that energy to work. Everybody tracking? They're kind of slippery concepts to wrap your head around. Yeah, something like this, right? Yeah. Yeah, it's a lot, kind of a lot. Honestly, if you can go through these slides, this might be good practice actually, going through these slides and try to explain like I'm doing now. Try to explain it as if you're explaining to somebody who doesn't know what it is. And if you can make those connections between each of the things, it'll make it easier to remember, because the reason that the coffee cup calorimeter measures delta H is because it allows for an expansion of gas. And if the gases expand against pressure, then it's doing work and you lose a small amount of energy. But being able to remember that chain of things is the tricky part. All right. Okay, so the change in enthalpy for a particular reaction. Change in enthalpy is for a particular reaction. So if the reaction changes, then delta H of the reaction also changes. And it changes predictably. So if we multiply our equation by some factor, that'll also multiply delta H by the same factor. So here we multiply this whole reaction by 2. So it goes from 1, 2, and 1 to 2, 4, and 2. And that makes sense, right? Because we're changing the coefficients. Of course, we're going to change essentially the coefficient on delta H. Twice as much things react, twice as much heat produced. You can also change the sign by reversing the chemical equation. So if in the forward reaction, it's a positive delta H, in the reverse reaction, it's going to be a negative delta H. And this is again because if we have an exothermic reaction, you're breaking weak bonds, forming strong bonds. If you go backwards, now you're taking weak bonds and you break them, and you take strong bonds and you break those, and you form weak bonds. That difference in energy is just going to flip. It's also because it's a state function. So the direction doesn't matter, just the initial and final state. So multiply by some factor. Now, Hess's law is sort of a special application of all of this. If we know the delta H or the heat of reaction for one reaction, we know the heat of reaction for another reaction, then sort of the combination of these two reactions will produce a combination of their heats of reaction. And this is because for every step, so for our hypothetical here, if we start out with A plus 2B, well, let me ask you, is this an exothermic or an endothermic reaction? Would the sign of this jump be positive or negative? Yeah, so endothermic. So the enthalpy goes from whatever this number is to a higher number. So it gets more positive. And then going from C all the way down to D is going to be exothermic. And it almost doesn't matter that we can do these individual steps, because the final result is the same as if we had just gone from our initial to our ultimate final step. In my mind, I was also kind of thinking of this like if you had sort of steps. If we start on some step, let me just put it here. So we start, I guess I'll just call this, I'll put it in here, A plus 2B, and then it goes up to C, and then it drops down to D, I guess 2D, right? Kind of the same thing if we're progressing in time this way, and this is still enthalpy. So this should be H. This is time. Right, so in your first step, you go up to a higher enthalpy, so positive, and then the next one you go down. The only thing that really matters is where you start and where you end. And we can do this, and this becomes really useful because we have standard enthalpies. It's 622 already. Yeah, so I guess this is what we're sort of leading into with this. The power of this, the reason that this is cool, is that it makes it possible to determine delta H for a reaction without directly measuring it in the lab. So if you've done separate reactions, or if you have a sort of, I was going to say textbook, but not a textbook, but like the CRC lab manual, which has just like tables of these reactions that somebody else did, measured delta H for, you say, oh, I'm going to do this reaction, it's going to react these things, and it's going to produce this. You can go through and you can pick out previously done reactions and combine them together so that you get whatever reaction you're going to do, and it will tell you if the reaction is going to be exothermic or endothermic, and how much heat it should produce sort of under ideal circumstances. Yeah, so, all right, well, we'll do the rest of this on Wednesday.